Okay, so we're carrying on with 6.3, Principle of Relativity. There really are quite a few videos for this one because there's a lot in here that's important. What we've seen thus far is that for any inertial reference frame, the delta V, the change in velocity, would be the same as it was in the Earth reference frame. If you look at the velocity in the Earth reference frame, velocity time curve, and you looked at the velocity time curve in any other inertial reference frame, then the delta V, that delta V is the same in both the inertial and the Earth reference frame, which means also the change in momentum is the same. So the delta V here was 0.4 for cart 1, and here again you can see it's 0.4 for cart 1 in the other reference frame. So the important thing is this, that the velocity is not the same, the momentum is not the same. Don't get confused. We are talking about the delta V and the delta P. The velocity does change if you change your reference frame, right? The cart 1 is 0 in the Earth reference frame, and in this reference frame, cart 1 is 0.2. So V does change, which means the momentum in a different reference frame does change. But delta V, delta P does not change. Okay, I hope that's clear. Now in this video, we want to ask, now what about delta K? Right? What about the change in kinetic energy? So is that the same in an inertial reference frame? Now what do you think? What do you think? Now the thing is, why is delta V and delta P the same? Well, because in a sense we're just looking at the values of the velocities. If this curve has just been shifted from this curve, then those differences are going to remain the same. But what is the equation for kinetic energy? K is half mv squared. So notice that little 2 there. That little 2 changes things for us. So for example, let's look at this. Let's look at this one here. Remember, this is figure 5.8, I think. So inertial reference frame and M reference frame. This cart 2 is 0.12 kilograms, and this cart 1 is 0.36. And so what is the velocity of cart 1? It is 0 before interaction. After cart and cart 2 is 0.8. Okay, we're just reading it off there. They interact, and this one changes velocity, goes to minus 0.4, as you can see, from 0.8 to minus 0.4. This goes from 0 to 0.4, 0 to 0.4. Nothing unusual there. The delta V is for cart 1 is plus 0.4, for cart 2 is minus 1.2. Okay, and as we've been saying now for a few videos, if you look at a different reference frame, an inertial reference frame, then the delta V's for each cart must be the same, right? The delta V's are the same in the different reference frames. But what about the kinetic energies? So look at cart 1 and cart 2 before they collide in this reference frame. Just go and calculate it. Half mv squared. Use this and you'll find that for 0 velocity, I've got 0 kinetic energy. For 0.8 meters per second velocity, I've got 38 times 10 to the minus 3 joules. Just go and calculate this. And then after they interact, you've got this velocity and this velocity, and you go and calculate the kinetic energy for each cart afterwards, and you get this. Okay, fair enough. Now, what is the delta K for cart 1? It is this. And what is the delta K for cart 2? It is this. It's plus 29 minus 29. So if you go and now calculate the same kinetic energies for these two carts before and after in the new reference frame, can you see that you get different? We understand that we'd get different kinetic energies, but look at the delta Ks. Can you see that the delta Ks are different? Here, the delta K for cart 1 was plus 29, and here the delta K for cart 1 is plus 58. Now why are the delta Ks different? It's because of this guy. We're squaring the values, the velocities. And the delta K for this guy over here is minus 29. It loses that energy. But the delta K for cart 2 is minus 58. So before, we saw that the delta V is the same, and which means that the change in momentum is the same. But the delta K is not the same for each object. But what is the same? What is the same? The delta K for the system is the same. Look, 0 and 0. So this is what we need to learn from this is delta K is not the same for each individual object, but it is the same for the system. Okay? So that is that. By the way, this is an elastic collision. Okay, that is an important point. Elastic collision. Elastic. It's an elastic collision. Okay, did you hear me say it was an elastic collision? Which means obviously that no kinetic energy has been converted into internal energy. But this is the point, guys. Delta K is not the same for each individual object in the way that delta V is the same for each individual object and delta P is the same for each individual object. But delta K is the same for the system, the entire system. Okay? Hope you're not too confused. Cheers.